So welcome to this session, and we're going to start out with Alex May from UBC, and he'll tell us about some quantum tasks and their relevance to holography.
Okay, great. Thanks, Mark. So I just want to start out by thanking the conference organizers for the invitation to speak today. It's great to have such a broad audience for this work. So what I'm going to speak about is ADS-CFT and what causally defined features in the bulk of ADS tell you about correlations in the dual CFT. Okay. So I'll start out by recalling a sort of classic setup in ADS-CFT, which involves choosing 4 points on the boundary of ADS. So the points here are C1, C2, R1, and R2. And the way I'm going to choose them is such that these points scatter in the bulk, but do not scatter in the boundary. And what I mean by they scatter is that there exists some point P in the bulk, which is in the future of C1 and C2, and the past of R1 and R2. So you can see that this point here has that property in the bulk, but that in the boundary, there's just no such point. Okay. So if you try and meet up, say between C1 and C2 like this, then you can get out to R2, but not to R1, or you could do this way and get out to R1, but not to R2. Okay. So this observation is a little bit puzzling in a way, because you might think that there's some physics associated with being able to meet up in the bulk like this. And it's puzzling how the boundary theory can reproduce the same physics without having that point. And this has been thought about productively by a number of authors, famously by these authors at HPPS, who understood that for the boundary to reproduce the bulk physics associated with this point, the boundary theory needs to be large n, and it needs to have a gap in its spectrum. Okay. So in this talk, I'm going to be thinking about sort of similar or analogous setups where there's some causally defined feature in the bulk that's lacking in the boundary. And what we'll think about is how do these bulk causal features constrain the state in the boundary as opposed to the boundary theory. Okay, so how does it constrain the state? And what we'll see is that these bulk causal features have implications for boundary correlations. Okay, good. Okay, so that's sort of the question for today, and here's how I'll go about addressing it in this talk. So I'm first of all going to recall some ways that you can measure correlations just in quantum states in general. And then since we're in a holographic context, those measures of correlation will have some interpretation in the bulk in terms of extremal surfaces coming from the Ryo-Takanaki formula. And then in the second and third parts of the talk, I'll state 2 theorems that begin addressing this question. So I'll state what's called the privacy duality theorem, and then also the connected wedge theorem. And what each of these does is relate some causally defined feature in the bulk to a different measure of correlation in the boundary. Okay. And as I go along, I'll try and explain how to understand why these theorems are true and where they come from. And that will lead us to think about quantum information and how it can move through and evolve in a space-time context. So I'll try and highlight that as I go and make more clear what I mean by that once we get into it. Okay, and then at the end, I'll wrap up with a few comments. Okay, so let me jump in talking about how to measure correlations. So there's going to be 2 objects that we're concerned with. The first is the mutual information. It's a measure of how correlated 2 subsystems of a quantum state are. So we're going to call those subsystems A and B. And the way it's defined is as the von Neumann entropy of subsystem A plus the entropy of system B, and then minus the entropy of their union. Okay. The second object that we'll care about is called the conditional mutual information, and it's defined as this difference of mutual informations. And the way that you should think about this is as the amount of correlation between system A with the union of BC that wasn't already present between just A and B, right? That's why we're subtracting off this second term. Okay, good. So those objects, those ways to measure correlation are built out of this von Neumann entropy. And we know that in holography, there's a simple way to calculate the von Neumann entropy using bulk degrees of freedom. So if I have some boundary subregion, which I'll take to be this region in orange here, V, the Ryuta-Kanaki formula tells me that to calculate the entropy, what I do is look at the area of some extremal surface that sort of encloses V like this, divide that by 4g Newton, and then add to that the entropy of the bulk fields in this gray region in here, where the gray region is the thing bounded by the extremal surface and V. Okay. So another thing to tell you about here is that if I give you the density matrix on the subregion V, what's been understood is that this records all of the bulk data inside what's called the entanglement wedge of V, that I'll denote E sub V. And I've drawn here. And the way that this entanglement wedge is defined is just as the domain of dependence of this gray region up top. Okay. And then this fact that this density matrix records all the bulk data in this wedge, I'll refer to as entanglement wedge reconstruction, and I'll use a few times in the talk. Okay. So the last sort of background thing to tell you about these measures of correlation is that the order of these correlation measures records qualitative features of extremal surfaces, right? So they're expressed in terms of the von Neumann entropy, and then the entropy is expressed in terms of the areas of extremal surfaces. And consequently, we learn things like if, say, the mutual information is order 1, that it implies that the extremal surface enclosing the union of A and B sits this way. And if it's order 1 over g Newton, then the extremal surface sits like this. Okay. Another way to say this is that in this case, the entanglement wedge is 2 disconnected regions, and in this case, it's 1 connected region. Okay. Good. Okay, so that's sort of the background and how I'm going to discuss correlation. Now I can state the first of these 2 theorems. So the first one's called the privacy duality theorem. And the way it works, at least roughly, is the following. So what we're going to do is pick a wedge down here. So this is the entanglement wedge of some boundary region, C. And then we'll pick another wedge somewhere up here, which is the wedge of some boundary region, R. Okay. And then what we do is we check if there's a causal curve from the wedge of C to the wedge of R that avoids the wedge of some third region that I'm calling U. Okay. When a curve has that property, that it avoids the wedge of U, I'm going to call it a private curve. Okay. And then what the theorem says is that if there's such a causal curve, then the conditional mutual information between V1 and V2 conditioned on U is order 1 over g Newton. Okay. I haven't specified yet how I'm defining the regions of V1 and V2, but you can get a sense of what they are from the picture. V1 is this, or is the domain of dependence of this blue region here, and then V2 is the domain of dependence of this blue region over here. Okay. So let me be a little more precise and tell you how V1 and V2 are defined. So to define it, start with the region U, and then draw a Cauchy surface that goes through the region U. So maybe something like this. We'll call that sigma. And then what I'll do is take the intersection of sigma with the space-like complement of U. Okay, and so that picks out, say, this interval plus this interval over here. Oh. And then looking at that interval, what I do is I look at the future of C, and I call the portion that's in the future of C, V1. And then the portion that's in the past of R, I call V2. or more properly, I call the domain of dependence of these intervals V2 and this domain of dependence V1. Okay, so that's precisely what I mean by V1 and V2. So now let me just say the theorem one more time now that you know what that is. So we're saying if there's a causal curve from down here to up here, then this V1 region and this V2 region are correlated in this precise sense. Okay. So we can see that this theorem is starting to address this question I started out with, in that it's relating some causally defined feature in the bulk, namely the existence of this causal curve, to a property of correlation in the boundary, specifically this conditional mutual information being large. Okay. Okay, so to understand this, and actually to understand various kinds of theorems that have this property that relate causal features and correlation, I claim you can use the following general sort of procedure. Okay, so the procedure goes in 3 steps, and the way it works is in the first step, you introduce some sort of probe quantum system that we're going to call Q, or in some cases we'll have systems QI. We introduce those to the bulk, and then exploit the fact that this causal feature exists to have Q evolve in some interesting way. Okay, so we're going to have something interesting happen to Q by virtue of this causal feature existing. Okay, and then the second step is I want to translate that evolution of the system Q to some evolution in the boundary. So I want to think about how does the quantum information stored on Q evolve in the boundary picture. Okay, and then in the third step, we think about that evolution in the boundary picture and note that in the boundary, we'll be lacking this same causal feature. And from that, we'll be able to argue sort of at the level of quantum information that appropriate correlations are necessary for the boundary to reproduce that evolution. Okay, good. So let me, so that was sort of the general picture. It's a bit high level and maybe sounds a bit vague. So let me go through those steps concretely in the context of this privacy duality theorem. Okay, so the first step is we introduce this probe system. We'll just need one here, we'll call it Q. We're gonna think about the state stored in the system Q, and I'm gonna call it psi. And then what I'm going to do with Q is record it into the bulk somewhere and send it along this causal curve gamma. Okay, so Q starts down here in the wedge of C. It travels through the bulk and ends up here in the wedge of R. Okay. And how I'm going to think about this is this sends the message, some message, which is the state psi, from the wedge of C to the wedge of R, and specifically it sends the message in a way that keeps it secret from the wedge of U, right? That was a property of this curve gamma, that it stays out of this region. And so we see that this message is sort of secret in a certain sense. Okay, right, and then the second step was we wanted to understand what does this mean in the boundary picture, okay? And we can use this entanglement wedge reconstruction fact to understand that. So what we learn is that, first of all, since Q starts out in the wedge of C, the state psi is initially available in this boundary region C. And then later, since Q ends up in the wedge of R, the state psi is available up here in the region R. And because Q stays out of the wedge of U, we know that in between, psi is never available in the region U. Okay. So another way to say this is that the density matrix on U is independent of the choice of state psi. Okay. So the boundary picture here is a little bit puzzling because again, we're lacking this sort of causal feature. In particular, all the causal curves from C to R are not private, so they all go through the region U. Okay, And so the puzzle is sort of how can we start with the information here in C, end up with it up here in R, but never have it pass through the intermediate region, right? And the resolution to this puzzle, you probably won't be too surprised to hear, is that the boundary exploits correlations among its subsystems to sort of hide the state on psi as it passes through the region U. Okay, and this is what in the end will lead to this requirement that this conditional mutual information is large. That's exactly the sort of correlation it needs to send this secret message. Okay, so I won't have the time to give you that argument in detail, but what I will do is try and at least give you a sense of how correlations among subsystems can be used to hide quantum states or quantum information. And the simplest way I know how to do this is using what's called the quantum one-time pad. Okay. So the way the one-time pad works is you prepare a string of random bits, which I'll call K. So maybe this is like 0, 1, ... And then we make a copy of K. So this is the same string, 0, 1, ... And what I'll do is I'll bring this copy of the string over here, which I'm going to think of like the region C. And I'll use K to pick a unitary, which I'm going to call P sub K, and apply it to the state psi. Okay, so I'm going to have some big set of unitaries I could draw from, and then which one I pick will be based on the value of K. This is going to sort of encode the state for me and hide the information, but it produces this state pk psi, and I take that and I just send it through the region U. Okay. Meanwhile, this string over here, I take through region V2 and up to what I'll think of as near the region R, and use my knowledge of K to do pk inverse and produce the state psi, right? And an important fact about what's happened here is that the string K never enters this region U. Okay, so from the perspective of calculating the density matrix on the subregion U, K is just unknown, and I should average over it. And what happens is if you choose this set of unitaries correctly, and then when you average over them, you'll just get the identity, which in particular is independent of your choice of state psi. Okay, so this, you can see, accomplishes what we wanted in that we start with the state down here in C, end up with the state up here in R, but in between it just looks like noise. Okay. Importantly though, the string K passes through region V2 here, and over on this end, just because of unitarity, and I brought K here, K has to go somewhere, and I don't want it to go in U, so it has to come up here into region V1. Okay, so as a byproduct of sending this secret message, we've ended up with K stored in V1 and V2, and so in particular, V1 and V2 are correlated. Okay, and yeah, so that's how we can see that correlations between subsystems help you send these secret messages. Now, what I've shown here isn't the most general thing you could do, okay? This is just one particular thing. But what you can show is that anytime you succeed in sending this secret message, this quantity, the conditional mutual information, is large, okay? And then that's what leads to the conclusion of this theorem. So to sort of summarize the reasoning, it's basically this private curve in the bulk lets you send a hidden secret message. There's no private curve in the boundary. So to reproduce that evolution, the boundary instead replaces the private curve with a large amount of correlation of this particular type. Okay, good. So that's the first theorem. Now let me give you the second example of this, which is called the connected wedge theorem.
Just chiming you about 5 minutes.
Okay, thanks. Okay, so the connected wedge theorem, I'll be briefer. The way it works is you pick 4 wedges, okay? So we have the wedge of C1, the wedge of C2, and then the wedge of R1 and the wedge of R2. And then what you do is you check if these wedges scatter in the bulk in some sense, okay? So in particular, you're gonna check if this region, which I'll call the scattering region, is non-empty, where the scattering region is defined by looking at the future of the wedge of C1, the future of the wedge of C2, the past of the wedge of R1, and the past of the wedge of R2, and intersecting all of those. So for instance, this point here is in the scattering region. And then what the theorem says is if this scattering region is non-empty, then the mutual information between two associated boundary regions, V1 and V2, is order 1 over G Newton. Okay. V1 and V2 are defined by looking at, so for V1, we look at the future of C1, okay, and then the past of R1 and the past of R2, and that defines this larger diamond here. And then similarly for V2, but you use the future of C2, okay, and you get this diamond over here. So again, we're seeing that some causally defined feature in the bulk, namely whether this scattering region is empty or non-empty, is telling you about correlations in the boundary, specifically this mutual information. Okay. Another way to think about this, given what I said earlier, is that this large mutual information is associated to the extremal surfaces sitting this way. Okay, so I won't give a detailed argument, but what's important is that this theorem also follows from the same strategy that I outlined before for the privacy duality theorem. The way that it goes roughly is you introduce two probe systems, which are going to be Q1 and Q2, and you make use of the fact that this scattering region exists to do some local unitary on Q1 and Q2. So you can bring them together because the region exists. You do some local unitary, and then what you argue is that in the boundary, for the boundary to reproduce that local unitary, it needs this large mutual information. Okay, so it's the same sort of idea where we're thinking about the dynamics of quantum information. Okay, so that's all the content I wanted to say. I'll just wrap up with a couple of comments. The first comment is that, in general, in ADS-CFT, we have this very interesting connection between geometry in the bulk and entanglement in the boundary. And I think, so that connection, as we usually understand it, comes from the Ryutaganaki formula, and it relates bulk extremal surfaces specifically to boundary correlation or entanglement. And what I think these two theorems taken together suggest is that there's another sort of connection between geometry and entanglement, which is between bulk causal features and boundary correlation. Okay, and instead of being given by the Ryutaganaki formula, the connection is given by thinking about quantum information as it moves in space-time in the way that I've tried to outline. Okay, so this sort of fleshes out the entanglement geometry connection in an interesting way. And I think by fleshing it out like this, you get various things. So one really simple thing that you get is you can just follow these implications through like this, right? Relate causal features to correlation to extremal surfaces and end up with a connection just between causal features and extremal surfaces at the end. And so this ends up being just a purely geometric statement, right? Between two bulk geometric objects. So you end up with just some interesting statement about ADS spacetimes. And actually in both the cases that I showed here, you can just use direct GR proofs to reach the same conclusion. Okay. Another thing that you get here is, we get this different geometric way of thinking about entanglement. And so you can kind of revisit problems that we previously studied using extremal surfaces and ask if this causal perspective offers something new. And concretely there, what I have in mind is in the context of black holes and island formation, usually we study extremal surfaces to see when the island forms. Here you can look for maybe a causal condition for an island to form. And indeed, at least in some toy models, my collaborator David Wakeham and I were able to find such a condition. So I think that's also an interesting direction moving forward. Okay, so that's everything. Thank you, and I can take questions.
Okay, let's thank Alex. So we have some questions. The first one I saw was from Pedro.
Yeah, can I just ask a quick question? Maybe it's naive, but I was confused that the dimension was not playing a role in the discussion. And as Sasha Zhiboyedov also pointed out in the chat, I was used to these pictures where, say, to localize a point in 5D, you need like 6 points in the boundary from this work of Sasha, Juan, and David. But here, dimension was not showing up at all. Could you comment a little bit on what I'm missing?
Yeah, so that's a great question. It's a little bit complicated. So the theorems, as I've stated them, are true in any dimension. But for say, okay, so let's say think about the connected wedge theorem, right? So I was drawing this kind of picture, and there's wedges, but we can just think about it as points for now. And there's something like this. And so what's important here is that there's a scattering region in the bulk, but not in the boundary. And what happens in, say, like global ADS in one higher dimension is that if you just have 2 input points and 2 output points, then whenever there's a scattering region in the bulk, there's also a scattering region in the boundary. When that happens, V1 and V2 will just overlap. And so the mutual information between them, you could think of it as infinite, or you could think of it as ill-defined. But yeah, so the theorem sort of becomes trivial when you don't have this fact that like the scattering region in the bulk is non-empty and empty in the boundary. So the theorem is true, but trivial in global ADS in one higher dimension. On the other hand, if you don't use global ADS, like say you use the ADS soliton, so the boundary is a spatial cylinder, then there's non-trivial configurations and the theorem applies in an interesting way. So yeah, I think with the connected wedge theorem, it's like a remaining challenge in the future to understand better, say, situations where we have 2 to 3 scattering, and then that would remain non-trivial in higher dimensional global ADS. For the other theorem, the privacy duality theorem, you can always find non-trivial configurations even in higher dimensions, basically because you have this flexibility of choosing the region U in a lot of different ways. It's sort of this extended region, and you can play with it to get what you need.
Okay, let's go to Hiroshi, I think was next.
Yes, so I thought that to derive these theorems from boundary perspective, you may need some information like large N or existence of gap. And I'm not sure where or whether they appear in your one-time pad argument, which I believe is about on the boundary. Could you explain?
Right. So actually, sort of an interesting thing about the way this reasoning works is you don't really need to know very much about the boundary. All I use about the boundary is that it's quantum mechanical, so it's unitary and relativistic, so it has these light cones. But yeah, the way the theorems work.
So you don't need a weakly coupled bulk dual.
Well, yeah. So you use the existence of the bulk. So say for this theorem, we say, okay, this scattering region in the bulk exists. We're going to assume some unitary can happen in the bulk, and then that says something about what happens in the boundary. And then what you assume about the boundary is just that it's unitary and relativistic, and then the argument goes through.
So is this like some kind of a toy or caricature of what's happening in the bulk? Is it really a boundary proof?
Okay, I shouldn't call the boundary proof a proof. There's a little bit of a loophole. You can prove it. Okay, so for this theorem, you can, in general relativity, prove that if the scattering region exists, then it implies the extremal surfaces sit this way. So this is a proof from the focusing theorem, right? This is just the geometric sort of argument. The quantum mechanical proof is, yeah, it has a little bit of a hole in it. I believe it, but okay, there's a bit of a problem. And the way it works is just doing what I said. So you're just saying, you know, from the bulk picture, you know that a certain evolution happens, you know, certain information ends up at certain places. And then at the level of quantum information, you can argue that this entanglement is necessary. And you don't use that you're large N or gapped or anything like this, just that you're, yeah, unitary and relativistic.
Okay, thank you.
Yeah.
Okay, so yeah, unfortunately, we should move on. So I'll invite the others with questions, perhaps to put the questions in the chat. So we should move on to Thomas